Good morning, everyone. Welcome to 9495 day 2. You can see at the top here where it says the ratio test for series without negative terms. So that's kind of the new test we're going to be dealing with today. We now have a number of ways to determine if an infinite series is going to converge or not. I have those listed here just so we can keep track of them. So the nth term test is a test for a series to diverge or not. So we can only determine if a series would diverge, and that's if it fails the nth term test. Yesterday, we talked about the harmonic series and how the harmonic series passes the nth term test, yet it still diverges. So the nth term test is really the nth term test for divergence. We can only prove that something diverges with that, and that's if the limit as n goes to infinity doesn't go to 0, and the limit as n goes to infinity is going to have to exist. All right, and better be the 0. We talked about geometric series. If it's a geometric series, if it is a geometric series, and we can identify that, then if our ratio has an absolute value less than 1, we know it converges, and we can actually figure out the sum for that one. And then yesterday what we did was the comparison test, which is the one that people tend to find the most challenging and try to avoid if possible. The integral test, if you have a series that can be written as an integral, then we can go ahead and do the integration of that. And then if the integral converges, then the series would have to converge as well. And then a P series, where if P is a 1, that's your harmonic series. And then we talked yesterday and showed that if P is less than 1, you're going to diverge. If the P is greater than 1, you're going to converge. And if you remember, a P series is this form here, where we have a variable raised to the exponent, and the exponent is your P. And then based upon what value that is, that'll tell you if we're converging, diverging, or whatever. Okay, so the last one today, or not the last one, but the next one today is what we call the ratio test. So it says let the sigma, so you're going to have your sum for a sub n, be a series where all terms are positive, and that if I did the original series, so notice a sub n is the original series, the original nth term, that's going to be our denominator. So when we set up this little ratio being a fraction, if you think back to when you would have done sums, differences, one of the words you would have talked about is a ratio, it's a fraction. And the denominator of that fraction is going to be the original a sub n. The numerator in this fraction is going to be an a sub n plus a 1. All right, and then we'll kind of show what that means here in a second. If we go ahead and set up that ratio, the original series on the bottom, the original nth term on the bottom, and then that nth term with an n plus 1 series on the top, you're going to calculate that limit. And when we do that limit, it's going to give you what we call, and don't ask me why they call this P as well. So notice up here, P series, we use a P, but the limit of this is also a P. So just kind of keep that in mind. And then based upon what that limit is, will tell us if our series converges or not. So if this ratio that we're going to set up right here ends up giving us a limit that's less than 1, then we know that that series is going to converge. If that P is greater than 1, then we know that series is going to diverge. And if that P, which is again just the limit of that ratio, equals 1, then we're kind of out of luck, because that is insufficient. It's not enough information to tell us what's happening. Okay. So let me first try to set up what this ratio means. So let's say I have the series that my first term is a 1, and then 1/4, and then a 1/9, and then a 1/16, so on and so forth. If you want to write that general term, all right, we could. All right, that would be the series 1 over n squared. Well, what a sub n plus 1 just means is if this is my first term and if this is my second term, then if I come up here, if n is a 1, then the subscript is actually a sub 2. So 1/4 would be our first term. If I go to here's n sub 3, but up here if I want n to be a 2, if n is a 2, then I actually want the third term, which would be 1/9, and then the next one would be 1/16. So what you can kind of see is the first term up here is actually the second term in our original series, and then the second term is the third term in our series, the third term here is fourth term in our series, so on and so forth. That's what this is showing here as the n plus a 1. We're just going to be one further down than what we would have. Okay. So if this has a limit that's less than 1, then that should be telling us that it has to be converging. As those numbers get smaller, if it's greater than 1, it's going to diverge. And then our number 3, if it equals 1, then we have a bit of a problem because we're not sure exactly what that means. All right, so let's jump to these and we'll kind of show how this gets set up. So when we go to set up the ratio test, what we're going to be setting up in your denominator is the original series. So this is your original series, the a sub n series. So you're going to put that there. In the numerator, we want the n plus 1 series. So if the original numerator was an n, it's now going to be n plus 1. And if my original denominator was 3n, it's now a 3 to the n plus 1. That's our ratio. What we ultimately eventually want to get to is what's the limit of this ratio as n goes to infinity. We don't really want to do that, however, until we've simplified this. So definitely we want to clean this up a little bit. So I'm going to take the original numerator, the n plus 1, divided by 3 to the n plus 1, and I'm going to multiply by the reciprocal of our denominator, right? When we divide by a fraction, you can multiply by its reciprocal. So we're going to do that here. Then the next thing we want to talk about, this will be really, really common with these, and I'll show it the first few times where it comes from, but eventually we'll just kind of jump right to this. But notice how this is a 3 to the n plus 1. Notice how we're adding those exponents. The reason you would be adding those exponents is because we would have had like terms getting multiplied by each other. So if I ask you to simplify this over here, that should become a 3 to the n plus a 1, which is what we have right here. So what we would see from this expression is that 3 to the n plus 1 can actually be broken up into a 3 to the n times a 3 to the 1. So I want you to do that, and that's going to be a common practice with this. The reason that benefits us is it's now easier to see sort of how this is going to play out, where if I'm multiplying, we can now cross multiply the 3 to the n's. And then what you're now left with is calculating the limit as n goes to infinity of an n plus 1 in the numerator, and then in our denominator, all we have is a 3n. We've been doing this a little more recently, but it's also something that we did at the beginning of the year. The limit as n goes to infinity, these are our little shortcuts with our exponents. So if you notice, I have a degree of 1 in the numerator. We have a degree of 1 in our denominator. So the limits just end up being their coefficients. So these coefficients, you'd have a 1 in the numerator, a 3 in our denominator. So this is a 1/3. So the limit of the n plus 1 series divided by the original a sub n series gives us a 1/3. If we go back to what the ratio test tells us, we just found this one, that the limit of that ratio is less than 1. That tells us that our series is converging. So what we would then do is, like with all of these now, hopefully we're getting used to this, understanding this is something we need to do. We're going to state if it converges, and then we need to identify how we knew this. And the reason we did know that one converged is because of the ratio test with a p equal to 1/3, which is less than 1. Like we talked about in the last few sets of notes, first state if it converges or diverges, identify what sort of test we used, ratio test, geometric series, comparison test or whatever, and then state what prereq we hit in order to make that determination. And in this case, it's our p was 1/3, and the good thing about that converging is that it's less than a 1. So that's your first ratio test. Hopefully we followed all of that. So if we go now to number 2, same process, where I'm going to put the n plus 1, or the original series, in our denominator first. So this would just be 1/3 to the n. And then in the numerator, I'm going to do 1/3 times an n plus 1. So that's our n plus series in the numerator, original series in our denominator. So as I clean this up, what we're going to be calculating is the limit as n goes to infinity. The numerator I'm going to distribute. And then in my denominator, I'm going to multiply by the reciprocal. If we simplify this, we really don't even need to. You could go ahead and evaluate that now. But just to make sure it's clear where this comes from, if I now ask you to evaluate this limit, degrees are both 1s in the numerator and in the denominator. So we look at our coefficients. coefficients here are 3. So 3 divided by 3 gives us a limit of 1. So that's our limit for the ratio that we set up. However, if you notice, if p equal to 1, that's somewhat problematic because we can't make a determination from that. We don't necessarily know if this converges or diverges. So we would then need to be able to understand a previous test or something maybe that we learned tomorrow that would allow us to determine this. So let's go back to this one. And what we're going to do is I'm going to rewrite this a little bit. And you don't necessarily need to rewrite this to understand it or be able to make the explanation I'm going to make in a second. But notice if I pull that 1/3 out or just ignore that 1/3 from yesterday, this should look very, very familiar to us because this is the harmonic series. So if this diverges, it doesn't necessarily matter that we're diverging a little bit slower. We'll just get to infinity 1/3 of the rate that the original harmonic series would have gotten to because of the 1/3 being there, but we're still going to diverge overall. So this one then ultimately we can say diverges. And then like we talked about yesterday, the harmonic series speaks for itself. So all we have to write is harmonic series. Like we've talked about yesterday and then moving forward, if you recognize this, there's really no need for us to do this. If we see that's the harmonic, use the one that's the quickest, most easily identifiable, and write that right away. But just wanted to give you one when we do a ratio test and see what happens when it's a 1, because that can certainly happen, and then we just need to explore some other options. So that's 2. Number 3, here's where the ratio test is pretty critical for us. When we start dealing with all of these factorials here, because any other method is pretty hard other than maybe the nth term test and determining whether or not that's going to converge or not. So with this, you almost certainly are going to be using the ratio test whenever you see these factorials. Okay, so let's go ahead, set this up. Hopefully I have enough room. I'm going to take the original series, that's my denominator. So I have n factorial, all divided by 2 n factorial in the parentheses here. Careful with your order of operations here because I was just about ready to mess that up myself. So just rewrite your denominator, your original series nth term in your denominator. The numerator, you're going to have an n plus a 1 first and foremost. And then we want our factorial. That's one of those. And then I'm going to need another one of those, an n plus a 1 factorial. In your denominator, our priority is the n plus a 1 first. So the first thing we're going to set up is an n plus a 1. And then that has to get multiplied by a 2. And then all of that is within a parentheses with a factorial behind it. Give you a second to get all that down, make sure we have everything in the right order. So then next, what we have with, I have an n plus a 1 factorial and an n plus a 1 factorial. Here's where things get a little bit interesting. So let me go on a tangent over here. So let's say I gave you n plus 3 factorial divided by n factorial. So we all know like 6 factorial is 6, 5, 4, 3, 2, 1 multiplied out. Well, what would n factorial be? Because if I know this is 6, then I know I start at 6, 5, 4, 3, 2, 1. Well, if it's n factorial, where do we stop? Shouldn't this start at 6 and then we just start subtracting 1? And we could write this forever, or eventually I could stop and then just put a factorial behind it and say that this would right now go on forever because we don't necessarily know what our n is. Okay, so let's say I ask you to simplify this guy up here. Both of these would technically go on forever, right? Like n plus a 3, if we don't know what our n is, n plus a 2, n plus a 1, n minus 1, n minus 2. And eventually we don't want to write those forever, so we'd put a factorial behind it. In my denominator, same thing would play out. I would do n, and then n minus a 1, n minus a 2. But notice how eventually we would start to see kind of a pattern. I'm going to put the factorial right here. So wouldn't these n minus 1s cancel? wouldn't the n's minus 2's cancel? And I'm going to cancel out the factorial to indicate all the subsequent terms would have also have canceled. Notice as well, the regular old n's would cancel. What we would be left with in this instance is this n plus 3, n plus 2, n plus a, 1. What I really want you to focus on, so we understand how we can simplify these, is what cancels. So notice how the n cancels, and then every term after that is going to cancel, leaving us with this. So here's what we really want to do when we simplify these. N plus a3 factorial. Let me do it one more time in a little more efficient way. I really only want to take this down as far as this goes, because I know then every subsequent term is going to cancel. So I would really just do n plus a3 times an n plus a 2 times an n plus a 1. But once I get to the end, let's stop writing them and let's put the factorial behind it, because then I have an n factorial in my denominator. So now I can keep writing these if I wanted, but wouldn't every term from here cancel out with every term that would produce? And what we're just left with is this. All right, same thing we were left with when we wrote all of these things out. So we really want to take the bigger factorial. We want to keep finding its subsequent terms until we get to a point where it would reduce with something else in our problem. So hopefully remotely, just watching a little video, that will make some sense. And as we do these, hopefully you'll kind of pick up on this. Let me now create some space because we got a little work to do here. So pause me if you don't have all this down. All right, so now let's go through this here. So the first thing I'm going to do, even before maybe we get into that, is let's just write this as two separate fractions. So I'm going to do an n plus a 1 factorial, an n plus a 1 factorial, all divided by, and then all I'm going to do is write this as 2n plus 2 factorial. So that's the n plus 1 term simplified a little bit. Then take your denominator. So now we're just going to take this denominator here and we're going to multiply by the reciprocal. So this would be a 2n factorial. And then I have an n factorial and an n factorial. Simplifying that right now, we don't necessarily know what cancels. If you do, that's pretty good at this point. We definitely want to go ahead and show a little bit more work. So here's this little n plus a 1 with a factorial behind that. So without knowing where to stop, this could become n plus a 1, n minus 1. We just keep subtracting 1 forever and ever and ever. Well, we can put a factorial behind that to indicate that that goes on forever. But we don't want to have to do that all the time. So let's go to n plus a 1 factorial. And instead of doing n plus 1, n minus 1, n minus 2 forever, not knowing where to stop, notice the denominators over here. Notice how there's an n factorial right here. So all I am going to do is take this n plus 1 factorial, and I'm only going to write enough terms until I get an n factorial here, because I know it would then cancel with the n factorial right over here. I wish I wrote that a little bit bigger. Let me create a little more space, because don't we have to do the same exact thing then with this guy? Because that would also produce this, but we don't want to go that far. So let's just do an n plus a 1 and then put an n with a factorial behind it, because we have another n factorial in the denominator. So we can stop here and that will reduce with this n factorial. Okay. All right, the next one. Let me find one more color here. Let's do that color. So this one, the 2n plus a 2 factorial, we could write that as 2n plus 2, and then we would do 2n plus a 1, and this could go on forever. But notice, if I stop right here and put the factorial behind it, indicating that it goes on forever, didn't we have a 2n factorial in the numerator, which tells us we want to stop right there, because then these and every term after that would cancel each other out. Again, hopefully this is making some sense here. The 2n factorials now, as we reduce this, will cancel. This n factorial cancels that n factorial. This n factorial cancels this factorial. then we're pretty close. I'm going to do an n plus 1 in my numerator. That's left. That's the only, there's actually two of those up there, aren't there? So an n plus 1 and an n plus 1 in the numerator. Notice down here, though, I'm going to factor out the 2 right here so that I created 2 and then an n plus a 1, and then I'd still have the 2n plus a 1. So the only two things left over were this one, and I factored the first so that it's easier to see that the n plus 1s cancel, so that finally, hopefully you still have a little bit of room, you end up with an n plus 1 in the numerator. You end up with a 4n plus 2 in our denominator. We are now ready to calculate this limit and pray to God that it's not a 1, and we did all of this for no reason, that we can't even make a conclusion out of this. When we do the limit as n goes to infinity, though, we can see hopefully that this should have a limit of 1/4, so that we can then say that this does converge because of the ratio test with a p equal to 1/4, which is less than 1. That's your first factorial. Let's revisit the original problem real quick, because usually if there's some people in class, and it's usually rooms full of pretty smart people, people think that we should be doing the nth term test first. Maybe I should be talking about that because I would have emphasized that yesterday in class. So we're always doing the nth term test first, and you're kind of always hoping that it doesn't pass the nth term test, because if it doesn't pass the nth term test, then we know it diverges and you're done. So that's nice. You're just over. So a lot of people think when they look at this, I have two n factorials on top, an n factorial multiplied by another n factorial, and we talked about how quickly factorials grow, that those two guys multiplied together would grow faster than a single factorial with just a coefficient of 2. However, the way we can determine which factorials are going to grow the fastest are not actually exponents, it's actually the coefficients. So the fact that this has a 2n factorial, this grows faster than a regular 1n factorial, even if they are multiplied together. Think about why that would be. If I have like 1 million, and in the grand scheme of things, 1 million is not all that big of a number. But think about 1 million, and then now think about twice 1 million, so 2 million, with a factorial behind it. And if you start counting down, 2 million times 1,999,999 times, and you got to keep doing that forever. Hopefully it's easy to see just how huge a 2n factorial would become as we go to infinity. Okay? So that's the ratio test. You might think it's a little weird at this point. Honestly, most people really like the ratio test as they get used to it because it works most of the time. So on the next page then, what we're going to dive into is any test. So now we have all those tests that we listed at the beginning of the notes. So if you go to the top of that first page, we have all the previous tests mentioned. Now we have a ratio test. And we can now use any test to be able to determine if the following series converge or diverge. Ideally, we want to be using the most efficient, quickest method. All right. First thing, however, as we talk about these, the first thing you are always identifying is, does it pass the nth term test? If it doesn't pass the nth term test, we know right away it diverges. So that's really your hope in almost all of them, is that, all right, it fails the nth term test, I'm done. We write that it diverges, we move on to the next problem. If it passes the nth term test, that unfortunately doesn't prove that it converges, and then we've got to explore all of these other tests that we have talked about. All right, so as we dive into number 6, this is still your first thought process, is can I look at that series and determine that as n goes to infinity, will this go to 0? And if it does, that just means we got to do more work. If it doesn't, it means it diverges. So hopefully you can kind of pause me with these and just see if you can figure it out on your own with all of them. Hopefully this one, you can recall that this is our exponential function. So as n goes to infinity, what this is going to equal is, is e to the first. So what that would then mean is overall, the series has to diverge because you're going to be adding e to the first over and over and over again. So this would diverge. You would then tell me what test we use. This is the n-term test. And then we would identify what was that limit. The limit as n goes to infinity for my general term was e to the first, which is not the 0 that the n-term test tells us we have to go to before we have any chance to converge. All right, so don't lose sight of the n-term test. I put this one deliberately first, so we know that's the first thing we always look at, and then we don't have to worry about all these other tests. All right, so now number 7. Hopefully we have done enough of these. One whole day of notes was dealt with this type of a function or series. Did a little bit more yesterday as we reviewed them, but hopefully we can now look at this and know that my numerator is always a 2, and your denominator has a base of 3 raised to the nth power. So that is classic geometric series. The numerator is always 2. Your denominator is going to repeatedly get multiplied by 3. So what we would hopefully be able to do is look at that and right away say that this converges because it's a geometric series. As you write that down, just remember what this would have given us. This would have been 2 over 3 to the 1 since I started in n as a 1. Then I would have got 2 over 9, and then 2 27ths, so on and so forth. So this is very much a geometric series if we just plug this in. And the reason it converges is because our ratio has an absolute value that is equivalent to, if we now look, aren't we multiplying by 1/3 every time? And that is less than 1. So that was the second type of series that we talked about, and I think it's probably the second easiest. The n-term test would be the easiest. Geometric is kind of the next one if we can identify that it is. However, let's do the ratio test on this real quick. And you don't necessarily have to write this down, but just to kind of show that there are different routes we could take with these. So I'm going to take 2, and a lot of people like the ratio test because of this, because it's now systematic. It's the same thing over and over and over again, versus having to think a little bit and figure out what method to use. So that's our n plus 1 series divided by the n series. So let's now take that denominator and we're going to multiply it by its reciprocal. And then this would equal 2 over, remember how we simplified this previously today, 3 to the n times a 3 to the 1. And then times a 3 to the n over a 2. We would then recognize that this cancels and the 3 to the n's, and what we would be left with is a 2 over 6. So now let's find our limit as n goes to infinity. You're left with a constant, and the limit of any constant is that constant. So 2/6 is your limit, / 1/3. The ratio test, that's your p. It's a 1/3. It's less than a 1. That would also have told us that it converged, and then we'd have to go with ratio tests, say what the limit is, and say that it's less than a 1. So a lot of these are going to have some options, and it really kind of depends on which one you're going to prefer. Let me write down nth term test. So we did that one. So that's another option. 8. I believe we've already done this one yesterday. Let me see here. Yeah. So let's see if we can kind of remember this. If you want to pause and see what we did here. But first and foremost, nth term test. Oh, I should have talked about that up here. Sorry. Getting a little rush trying to make these. First, this has to pass the nth term test. It obviously does, right? Because we said that it converges. So if we look, this is our whole which function grows the fastest. So a exponential function 3 to the n grows incredibly fast, and you have a constant in the numerator. So this absolutely would have passed the nth term test. It would have been going to 0 at the beginning. That's why we would have had to continue on. So when we go to number 8, that's your first thought process, is does this even pass the nth term test? So with this one, we talked about it yesterday, it does, because what's going to happen is on the inside, if we just ignored the exponent, As n goes to infinity, the inside is going to behave more and more like a 1/3. And then if I get 1/3 to the n, then 1/3 to the n can be rewritten as 1 to the n over 3 to the n, which is really just 1 over 3 to the n. And then that should definitely be passing the nth term test, so going to 0. Passing the nth term test doesn't guarantee you converge, however. We would definitely need some other route to kind of confirm what that is. I deliberately wrote it like this, same way we would have written it yesterday in terms of how we're going to be able to talk about this. Really the only way to go through this. You could try the nth term test. It's pretty ugly. I actually don't even think it's going to work out particularly well for you. It's certainly not a geometric series. It's not a p series. If you try to integrate that, that's going to keep you busy for a very, very long time trying to figure out a way to find an integral of that. So the only other way that we were left over is your comparison test. So when we talked about the comparison test in class yesterday, what we would have said is that we really just want to tweak a little bit the original function, and usually the numerator or your denominator. So the easiest thing to do is really to drop a constant. So if we see this little plus a 1 here, I'm going to rewrite this so that this is n over 3n, all to the nth power. Think about what that would then mean if this denominator is always 1 unit larger than this denominator and everything else is going to be the same. Then the denominator always being bigger should always make this overall value ever so smaller than this one. Then, don't these really just cancel, leaving us with a 1/3 inside of the parentheses. So this is really equivalent to 1/3 to the nth power. So what we were really doing when we said our original series is less than this guy, we were actually comparing it to a geometric series that we know would converge, because this geometric series would have had a ratio of 1/3. So by way of the comparison test, this should converge. Write your test that we did. So here we did the comparison test. And then we would say it is less than a geometric series with a ratio whose absolute value is 1/3, which is less than 1. So since we're less than a convergent series, then that series itself would have to converge. Number 9, as n goes to infinity, these both go to 0. So we definitely pass the nth term test. With this one, I'm going to go ahead and split this up just because I can. But it also gives us a little talking point here. So go ahead and split that up. And then what I'm going to do is come back up here. What we just did is the comparison test. The one that we haven't talked, or one of the two that we haven't talked about yet, is a p series. And for the first time in this set of notes, we have a p series. So when I have a constant over n to a power, this is your p series. So what this actually does by itself would converge, like a p series with that p greater than a 1 is going to work. It's going to converge. However, since it is part of a bigger problem, notice how this guy is the harmonic series. So if we know that this sum is going to be huge and just get larger and larger and larger, it doesn't matter that we're going to subtract. Let's say I think that actually converges to 1 if I remember correctly. But let's say if we subtract 1 all the time, it's still going to infinity. It's just going to go there ever so slightly smaller because it's going to be 1 smaller than what it would have normally have been. So when we see something like this, as long as you see the harmonic series, and I see the harmonic series right here, you don't even really need to split it up. We can say right away that this diverges. And then harmonic is also nice because you can just write harmonic series and there's really no more justification needed. 10. this one is on your previous set of notes, but if I had to guess based upon timing, we're probably not going to get to that one. So this will be the first one that we would do here. And on the set of notes, I ask you to integrate that. Still can do that, but if I remember correctly, the ratio test also works nicely here. So let's first rewrite this so that we have an e to the n. If I had you integrate this yesterday, and we're not going to go all the way through it, but as a quick little refresher, hopefully we remember this method. This is the integration by parts shortcut. When we did the tabular integration, and then we connect all these, everything works out nicely, so on and so forth. But we now have a new method. Maybe we'll get to it yesterday. Maybe we got to it yesterday, maybe we didn't. The new method that's going to make this a little bit easier is the ratio test. So we're going to set up our ratio. We're going to do the n+1 series in the numerator. And then eventually, as in right now, instead of dividing by the original, so instead of dividing by this, you can certainly set that up. Every single time when it's a fraction, we got to multiply by the reciprocal. So let's just jump right to multiplying by the reciprocal. We then have an n+1 squared over, I'm going to simplify this to be n to e to the nth times an e to the 1, and then multiply that by e to the n over an n squared. What we then have is the e to the n's canceling, and we are left now with an n plus a 1 squared over n squared. Uh-oh, I'm not liking what I'm seeing here. n+1 e to the n+1 times m. Because that doesn't give us our answer, does it? Yeah, it does. Sorry, I forgot the e. So this guy should be right here. I was afraid that was going to give us a limit of 1. I don't remember it being a limit of 1. Remember, if we do the ratio test and you get a 1, that's indeterminate. We've got to do something else, and maybe we're going to have to do this, and I was panicking for a second. However, we forgot this e. So now if we go ahead and do limit as n goes to infinity, so limit as our n goes to infinity right here, same degrees, so we're going to look at their coefficients. This has a coefficient of 1. Your denominator has this coefficient of e, so the limit is 1 over e. That is less than a 1. And then the ratio test, that means that we converge. So put that over here. We converge. Ratio test with a p-value of 1 over e, which is less than 1. All right. (11). First thing we want to do, make sure that it passes the n-term test. I think I may have forgotten that again in number 10, but hopefully when we would have done the n-term test with this, as n goes to infinity, your faster growing function is definitely on the bottom, so that would have had a limit of 0. When we go to number 11, the reason we don't want to forget that, and that's twice now I've forgotten it, is because when we do it here, now we should know factorials grow faster than exponentials. So the faster growing function is on top. That means that this has a limit of infinity. So this is a nice one that we could say diverges right away. And term test, the limit as n goes to infinity for our general term is infinity, which is not the 0 that it's supposed to be. All right, we got 2 more. All right, number 12. First things first, we want to go ahead, do the limit as n goes to infinity. Definitely does, because you have a constant on top, and then we have all of our variables in our denominator, so this will definitely overall have a limit of 0, which is somewhat unfortunate, because when it doesn't, like in number 11 that we just did, then it's quick. We just say right away, it diverges in term test. So when we look at number 12, and again, if we were in class, I'd probably have you try this one. So if you want to see for anywhere close to understanding what the heck's going on with all of this stuff, when you have all these options to choose from, could pause me and kind of think about what maybe you would do here. your list of all of them that I have up here. There's actually one that I haven't written down yet that we haven't done yet. That is the integral test. So let's put that in there. I think that's all of them that we need right now. You could pause me and then see if you can figure this one out. All right, so if you're just plowing through, then you haven't tried it. If you did, what a lot of people try and do right now is the comparison test, which is a good thought because what they recognize is here's a 1 over an n, and I know that that is a divergent series. If it's a divergent series, what we're then hoping for is that our series is greater than the harmonic series. If it is, then it diverges. So that's kind of what we cross our fingers for. However, what we're going to find is, isn't this extra stuff down here going to make our denominator bigger than the harmonic series? So if they have the same exact numerator and this has a bigger denominator, what really is true is the series we are dealing with is less than the harmonic. And if it's less than a divergent series, we talked yesterday how that is inconclusive. We don't know what that means. So unfortunately, if you thought that, it's a good thought. It just doesn't give us enough information. So just because we haven't done this one yet, I want to make sure we got a little bit of everything today. This is the integral test, whether we recognize this or not. So the way we're going to integrate this, we're going to first set up the integral 1 to infinity over 1 and then the n. You could really write this as x if you want, because that's really what we're now dealing with. And then this is going to be your b. And this is an old u substitution problem. Let u be the natural log of x. And then du is going to be 1 over x dx, which is nice because this little 1 over x dx that we got here is exactly what we would have needed. So let's go ahead and substitute in. I would have had 1 plus u squared, because u was the natural log of x. I would have had the 1 over x dx remaining, so like I just highlighted here. And that is equivalent over here to your du. So if we get rid of, or if we plug in our du, then we get rid of the 1 over x and the dx. If you recall, since we just went from x's to u's, we need now new limits. We get our new limits with this right here. So take your b, substitute that in. It just will give you the natural log of b. If you take your 1 and plug that in, the natural log of 1 is a 0. We then need to integrate this, evaluate it. Hopefully we recognize this as the derivative of the inverse tangent, hopefully. So the antiderivative of that then is simply the inverse tangent of u from 0 to the natural log of b. Throw in your upper limit, subtract lower limit. We know the inverse tangent of 0 is 0. So then what we now need to do, and I probably should be better myself with this, when we set these up, what we're now looking for is what's the limit of this. Since b can't really be an infinity, we're just looking and evaluating this as a limit problem. So these should have been here all along. Because now this is how we then calculate if this is a convergent value or a divergent value. So let your b become infinity, right? That's what this is saying. So as b gets bigger and bigger for the natural log curve. So what that's just saying, envision the natural log curve. The natural log of 1 is 0. The natural log of curve looks like this. So as we go further and further and further right, so that's what this going to infinity means. Doesn't the natural log curve, even though it does it slowly, the natural log curve does increase forever. So overall, the natural log, as our b gets bigger and bigger, the inside of this parentheses is going to grow unbounded. So it's going to get bigger and bigger and bigger. As that gets bigger and bigger, what we're trying to evaluate is what happens to the inverse tangent graph as the inverse tangent graph goes further and further right. So I hinted at this a while ago. I didn't hint at it. I told you this flat out. This is going to get revisited in this chapter. Remember, the inverse tangent is the one that looks like this. You can throw that into your calculator if you want to confirm. here's what this inverse tangent graph looks like. And it's hard to tell whether or not we increase forever, but what we showed through that with the 1-to-1 and the range of inverse tangent is that this does actually level off towards pi over 2. And then down here, it's a negative pi over 2. So the inverse tangent, as we go further and further right, so as x's go to infinity, and that's what this is saying, the inverse tangent graph should level off towards pi over 2. So since this converges to pi over 2, that means finally, after all that work, we can say that our series converges. And then like we talked about when we did the integral test, as long as the work is there to justify it, so as long as we have all the work above it, which we do, then we can simply write integral test. All right. Okay, last one. 13. First, make sure it passes the nth-term test. Do not forget that, like I've done twice already. In this case, though, it does. Our faster growing function is on the bottom, so the nth-term test, as n goes to infinity overall, this goes to 0. Again, if you wanted to pause, try and see if you can do one on your own, feel free as we look at this one. But we now want to kind of figure out what this is. A lot of this is a process of elimination. This is one that definitely is not a p-series because you don't have a constant in the numerator. It's not geometric, so you're not going to be able to do geometric series. You may have illusions of integrating that, but you can't. So there's not a lot of ways that we could approach this one and be able to get very far. So what most people do at this point, what we're really left with, I just kind of eliminated a lot of them, is the ratio test and the comparison test. By and large, most people like the ratio test better because it follows the same pattern all the time. So let's go ahead and do the n+1 series. And then I would divide by the original series. But let's save a little time here. I've gone on long enough. Let's multiply by the reciprocal of the original instead of dividing by the original. This is tricky. So this is something you want to recognize. Normally, I don't know how I'll handle the quiz on this. There's a question similar to this. Let me rewrite this just a little bit so that hopefully this would make some sense. So I'm going to put the natural log of n+1 over the natural log of n, and then I'm going to do an n plus cubed. I'm going to leave that in this numerator, and I'm going to just take the n+1 and put it into the denominator with n plus cubed. So I just rearranged a little bit. Same numerators though, same denominators. Although I rewrote this wrong, so give me a minute. So for right now, let's ignore this. And if I gave you and asked you what remains, what is the limit as n goes to infinity for just this guy here, wouldn't we look at those exponents, say that those exponents are the same, and the coefficients would determine our limits. The coefficients are 1. So this all by itself is a 1. Here's bigger picture understanding this. The reason that's a 1, think about if I did 1 million and I cubed it, and then I did 1 million plus a little 1 and cubed it. Wouldn't that little plus 1 be so insignificant that it really has no bearing on this overall answer, which is why ultimately this would have a limit of 1. So let's reintroduce this guy. Along those same lines, let's say I did the natural log of 1 million and then 1. So the natural log of 1 million and 1, and then I divided that by the natural log, and you can do this on your calculator if you don't believe me or you just want to confirm, of 1 million. Wouldn't this little extra 1 right here, and again, 1 million in the grand scheme of infinity is nothing, wouldn't that little 1 have pretty much no significance whatsoever on the overall value compared to this guy? So if you throw that into your calculator, this has to be approaching 1 as well. So if this behaves like a 1, this is going to behave like a 1. What we get, unfortunately, is a 1 with the ratio test. So a couple things there. Ratio test is good. When you see these natural logs, that's something you want to understand. That is normally, in a normal year, a little question that I test you on our quiz. So if we go through with the quiz, then you're going to see that again. But it doesn't work because in the ratio test, if you get this 1, then you do all that work for nothing because that is inconclusive. So the only thing left over is this guy. So in some way, shape, or form, we want to be doing our comparison test. To me, this is a pretty tricky one to do the comparison test with. Some comparison tests are okay. A lot of them are pretty sneaky. So what we want to do is, again, just simply tweak a numerator or denominator. So all I'm going to tweak is I'm going to get rid of the natural log. So do that first. Now your denominators are the same. So really the denominators don't really have much of an impact in terms of what's going to happen to the overall value of this number. And the numerator here is always going to be bigger than a natural log of n because natural log of n grows very slowly. The n is going to grow faster than the natural log of n. So what that means is the one on the right has to be bigger, which means the one on the left obviously is smaller. So the series we're concerned about is less than n over n cubed, but notice what that really is. Isn't that, as we reduce it, reduce down to a 1 over n squared? 1 over n squared is a p series with a p of 2, and that's a convergent series. So what we've just shown is that our series is in fact less than a convergent p series. So if we are less than a converging series, then our series would also ultimately then have to converge. And we did that through the comparison test. And it was less than a p series with p equaling a 2, which is greater than 1. And in a p series, that is a good thing. Ratio test, that is a bad thing. So that's something to keep straight. They're both p's. In one case, less than 1 is good. In one case, greater than 1 is good. Okay? Hopefully this makes some sense. It's probably nice to have on video. It's a nice one to kind of look back and try to process as we learn all of these tests and realize that there isn't a set way to do these. You have to look at the series and then really have an idea of how to identify what test to use. And in many ways, for many of them, it's a little bit of guessing and checking, which is always kind of a crappy way to approach problems when we don't have an exact method to always go to. It makes it a little more difficult. So with that, if there's any issues, I guess tomorrow morning I won't be there, Wednesday morning I won't be there. Just check in with me at some point, because when we move on Wednesday, I'm going to kind of expect that we have seen this and know what's going on with all of it. Okay? So with that, we'll say goodbye, and we'll see you guys next time. All right, have a good day.